All right, I wanted to make a video here for pre-calculus to just kind of give you guys one final idea here, one final thought on limits so that you could watch this, get ready for this. That way we're ready for a test over limits. There's four major concepts I want to talk about real quick that we explored with limits. One we found was graphically. So we talked about looking graphically at limits and exploring what the graph looks like as we approach a value we called C, as we approach C from the left or the right or from both sides. So I want to briefly talk about that. We also talked about finding limits algebraically. I think I spelled that right, maybe. Anyway, so that's using either the factor and cancel out technique, multiplying by the conjugate, combining fractions and getting something to cancel, that kind of technique to help us find limits. And I also want to talk about continuity. When graphs are continuous is a really important part. And remember we talked about removable discontinuities versus non-removable discontinuities. So I want to do a quick review over what contributes to continuity of a graph. And also I want to talk about infinite limits and how infinite limits come into play, and a lot of this deals with asymptotes, so we'll explore that a little bit. So as we go throughout this video, there's going to be a lot of examples that I talk about and do, and if at any point you want to pause and try the video or try the problem on your own and then hit play again and see if you got it right, that would be a good opportunity for you to practice some of these problems to get ready for a test. All right, first exploring graphically. Remember, graphically is the idea that this limit is as x approaches 4. And if I just plug in 4, I'm going to get 4/5 minus 4/5 over 0. So I plugged in 4 for x, I get 4/5 minus 4/5 over 0. So that's 0 over 0. So this is obviously a problem. This is an issue. So this is where we said we want to take a look at the graph of this. So if I pull up the graph real quick, here's the graph of this, and I typed it in my calculator under y equals, just so you see. There it is. Make sure you got lots of parentheses when you type a function like this in. Anyway, it's hard to see, can't really see a whole lot, so I'm going to just remember use the trace feature. So if I want to see what happens at 4, I realize there's nothing happens at 4. So that's this whole idea that we say, well, here's 4 is somewhere right around here. Let's approach 4. Let's get close to 4 from both sides. So 3.9, 3.999, and then from the right side, 4.1, 4.01. And to do that, we could use the trace feature again, and we can plug in 3.9 and see what happens. We can plug in 3.99 and see what happens. We can plug in 3.99999 and see what happens. And notice we're going to 0.04, it seems. So let's try the other side. If we plug in 4.01, and we go in 4.00001. It looks like we're getting closer to this 0.04. 0.04. So it appears that the limit is going to be 0.04, which is 0.04 is 4 hundredths, right? 4 divided by 100 is 0.04. So it appears that the limit is 4 hundredths. Based on using the graph. And I also typed this next problem in here again. Notice this next problem, if we plug in -3, we get a 0 on the bottom. If we plug in -3 inside, we get a 4, and the square root of 4 is 2. 2 minus 2 is 0. So I also graphed this one in my calculator. I just got to turn this first one off, turn the second one on, and hopefully the graph, so get a nice view of this thing. And again, you can't really see a whole lot, but we know that something's going on. If you really want to try to zoom in, you can here. You get a little bit view, but then we kind of lose the -3 as it's off the graph a little bit. So I got to go to window, and I want to change my x-min to maybe -4, just because I want to capture the -3 that I see here. So here's -3, and something's going on there. So when it trace -3, and nothing's there. So again, I want to approach -3 from both sides. So -3.00001, and it looks like I'm getting closer to, looks like -0.25 possibly. Let's try the other side, -2.99999, and looks like, yeah, -0.25. So it looks like the limit of this is negative 0.25, which you guys should know is negative 1/4. So that's again how the calculator can use this to help us identify graphs of limits graphically, and make sure that your fingers come together at those points or else the limit does not exist. So here's a couple more problems. Here's some pictures of some limits so we could talk about this. First one here is approaching 1. So as x approaches 1, what's the limit doing? Well, notice that this is what we call a displacer or floating point. So if x is not 1, we're going to use this quadratic, x squared plus 2. If x is 1, we're going to use 1. So if I said what happens at 1, that would be 1. I mean, look at the point there, 1, 1. But as we approach 1, if I'm asking about the limit as we approach 1, as I approach 1, I'm closer to 3. As I approach 1 this way, I'm getting closer to this hole, which is at 3. So the limit is 3. But at 1, it's where the solid dot is. So we've done problems like that before. Here's another one. This one, clearly the limit does not exist. Okay? At 3 here, here's 3 right here. As I go from the right, I'm going up, 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 up. As I go from the left, I'm going down, 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 down. The limit does not exist. My fingers aren't coming together. Here's another one with an absolute value. Anything greater than 5, I'm going to be at 1. If I put a number greater than 5, I'm going to get a number over itself, and that's going to make 1. On the left-hand side, I'm going to get a negative 1. The top will stay positive because of the absolute value, but the bottom will stay negative. So again, my fingers aren't coming together here. So here's another example of the limit does not exist. Here's a trig function, secant, and you see these asymptotes, but be careful. We're talking about as x approaches 0. So as I approach 0, and as I approach 0, my points, my fingers are coming together right here at 1. So it does have a limit at 1. Here's another one. Here's tangent. Here's a bunch of tangent. The tangent function is a bunch of asymptotes. And I'm approaching pi over 2, which is right here, pi over 2. And notice on the left-hand side, I'm going up. On the right-hand side, I'm going down. So that's a nice example where the graph shows that the limit does not exist. So some easy examples there to understand graphically how to find limits. Here's a last problem that deals with graphs. I love problems like this. We explored one like this in class here today, where I give you a picture and I just ask you a bunch of questions. So first question is, what happens at negative 2? At negative 2, nothing. That does not exist. There is nothing at negative 2. Notice that's an asymptote. Okay. What happens as I approach negative 2? What's the limit as I approach negative 2? Well, as I approach negative 2, this side's going up. This side's going down. It appears that the limit does not exist there either. Interesting. Okay. What happens at 0? At 0, here's 0 on the x. We're looking for the filled-in dot. It appears to be 4. There's a hole here, but the filled-in dot appears to be at 4. What happens as we approach 0? What's the limit as we approach 0? Well, look at here. As we approach from the right, I'm down here. As I approach from, I'm sorry, that was from the left. As I approach from the right, I'm up here. The limit does not exist. Now, a little bit later, we're going to talk about one-sided limits. And this is a good problem to see one-sided limits. From the left-hand side, the limit at 0 does appear to be approaching. It looks like 1/2 maybe down here where that open dot is. From the right-hand side, it's approaching 4. It appears to be approaching 4, but overall, the limit does not exist. What's f of 2? At 2, well, here's 2 right here. I don't see any filled-in point there at 2, so there would be nothing there. There is nothing at 2. What happens as I approach 2? Oh, it's a different story. As I approach 2, I'm getting closer and closer to this hole. My fingers are coming together. Looks to be at a y value of about 1/2. How about at 4? Ooh, there is an open or a filled-in dot at 4. And I also see this asymptote at 4, but there is a filled-in dot at 4. So at 4, my function appears to be at 2. Now, what happens as I approach 4? Well, as I approach 4 from the left, I'm going up and up and up. As I approach 4 from the right, I'm going up and up and up. So the limit does not exist. However, since both sides are going up, I would also accept an answer of infinity. You could say the limit is approaching infinity because both sides are the same. So that's a nice, easy example. Hopefully that makes sense. I like problems like that. You'll probably see something like that on a test. All right, now for algebraic limits. Now, I gave you a bunch here. We're obviously not going to spend the entire class doing these, but these are supposed to be easy ones. These are easy ones. Plug in, chug. Plug the number in, get an answer. These are just using our basic idea of limits. All right, so these problems, again, are supposed to be pretty easy. So, like, for example, number 5, just plug in 2 to the 4th. The limit is 16. Very, very simple. So this first one will be 16. And if you want to pause this and try a couple of them out, they're most supposed to be easy. Look at 16. Plug in 3. On top, I get 6 minus 3 is 3. On the bottom, I get 8. So there's my answer, 3/8. How easy is that? Look at 20. Plug in 4. I get the cubed root of 8. The cubed root of 8 is 2. That's an easy one. Look at 17 here. Let's see here. Plug in 7. I get 35 on top. I get the square root of 9, which is 3 on the bottom. 35 thirds. Very easy. So that's the basic idea with most limits. Just plug in, get an answer. Nice and simple. Okay. Here's another set of limits where we're going to use our rules here. So this is nice and simple. I'm telling you the limit of f is 3/2. I'm telling you the limit of g is 1/2. And now I just want you to use those. So A says, what's the limit of 4 times f? Well, if the limit of f is 3/2, then it'd be 4 times 3/2. And 4 times 3/2 is 6. Nice and easy. All right, how about the limit of f plus g? Well, that would just be the limit of f, which is 3/2, plus the limit of g, which is 1/2. So that's going to be 4/2 or 2. Nice and simple. How about the limit of f times g? Well, that would be the limit of f, which is 3/2, times the limit of g, which is 1/2. So I get 3/4. Another simple problem. Division, the limit of f is 3/2, divided by the limit of g, which is 1/2, times by the reciprocal, you get 3. So nice and easy. Those are supposed to be easy limits. I'm just trying to give you f and g, and then you use them to follow the rules. All right, now we're going to talk about our algebra, solving limits algebraically. Got to do some algebra to solve this limit. Notice if I plug in 3, I'm going to get a 0 over 0, which tells me that there's a hole here. So I need to use some algebra to help me out, and the key is to factor and get something to cancel here. All right, so let's see here. The top is going to factor into -2 and a +3. The bottom is going to be x minus 3 and x plus 3. That's an easy one. So this is what's going to cancel the x plus 3. So that means that -3 is a removable discontinuity. +3 from this guy right here is a non-removable discontinuity. That's probably going to end up being a vertical asymptote. So again, the key question is, though, is once these cancel, all that's left is x minus 2 over x minus 3. So to find where the limit is as x approaches -3, plug -3 in to this nice reduced answer. So that's going to be -5 on top, -6 on the bottom. There's my answer, 5, 6. Very, very easy. How about this one here? Let's see. Let's factor x 4, x 1, minus, both minuses on the bottom. Let's see, x 4, x with the 2. That's going to be a -4 and a +2. And now the x minus 4 cancels. That means at 4, I have a removable discontinuity. And at -2, I have a non-removable discontinuity, which is going to be a vertical asymptote. But anyway, now that I got my problem to cancel, I'm going to find the limit as x approaches 4 of x minus 1 over x plus 2. Now I just got to plug in 4, and I get 3 over 6. So my limit is 1/2. So it's all about being able to use algebra to get something to cancel to help you out. All right, sorry for the giving you vertigo there. Here's some square root one. With a square root problem, you want to be able to multiply by the conjugate. So here I'm going to multiply the top by the square root of x plus 5 plus 3. And I'm also going to multiply the bottom by the square root of x plus 5 plus 3. All right? So let's see here. That's going to give me the limit as x approaches 4 of x plus 5 minus 9 over x minus 4 was on the bottom. And now I'm going to have this square root of x plus 5 plus 3 down there as well. And now notice that on top, that is going to reduce to x minus 4. And that's actually very nice because that very conveniently is going to cancel with the x minus 4 that's on the bottom. So those cancel. And I'm left with the limit. And again, that made 1. They don't cancel, make 0. They leave a 1 there. So at the limit, and on the bottom here, I have this x plus 5 plus 3. And now I can replug in 4. And let's see, I'm going to get 1 over 4 plus 5 is 9. Square root of 9 is 3. 3 plus 3 is 6. So I get 1/6 as my limit. Here's another one working with fractions. Remember the key with fractions to get a common denominator. So my common denominator is going to be 4 times x plus 4. And again, the book uses this. It's a little bit easier to write. But if you want to rewrite that as 1 over x plus 4 minus 1/4, so you could see it a little bit better. Go ahead. So this first guy needs a 4 on top, so I'm going to multiply that 1 by a 4. Minus this last guy, he needs the x plus 4 on top and bottom. So I'm going to distribute a negative 1 through that x plus 4. So that's going to be negative x minus 4. And then instead of dividing everything by x, I'm going to times it by 1 over x. This makes a little bit work a little bit easier for me. So those negative 4's cancel, and I'm left with negative x over 4 times x plus 4 times 1 over x. Now those x's cancel. So now I got the limit as x approaches 0, and I got negative 1 over 4 times x plus 4. Very, very nice. Now that I got that problem to cancel, I could replug back in 0, and I get negative 1/16 as my limit. So that's how to do those fractions ones algebraically. We did a lot of those in class, but I just want to make sure everybody remembers how to do those because we got to keep up with that. All right, now here's another one that involves this delta x. You may see this on the test, and I don't want it to freak you out. Remember, that's just another variable. Don't let delta x scare you. We use h in class. So if you'd prefer to make that an h, you can go ahead and rewrite this as the limit as x plus h squared minus x squared over h. It's just a variable. That's all. Don't let it mean triangle times x. Don't let it try to confuse you. So remember, with this problem right here, I need that h on the bottom to cancel. So let's say it's going to be x squared plus 2xh plus h squared minus x squared, all divided by h. So the negative x squared, positive x squared cancels. So I get 2xh plus h squared all over h. I want that h on the bottom to cancel. So I'm going to factor out an h. And then that h cancels, making a 1, which is really nice. Now I could replug in 0. And when I replug in 0 for h, I get 2x plus 0, which is just 2x. So my limit there is a nice 2x. Now we've worked a lot with that with finding derivatives, but hopefully that problem makes a lot of sense as well. All right, here's some more pictures so we can explain what's happening here. Remember, in all these limits were happening as we approach c. So as we approach 3, notice at 3, I'm at that solid dot of 1. Here's the point, 3, 1. But it's the limit as x approaches 3. That happens as we get closer. So as I go from the left side and the right side, I'm getting close to this hole right here, which is at 0. So the limit would be 0. So that's the limit. At 3, I'm at 1, but the limit is 0 there. So that's that displaced point. Number 4 shows another one of these displaced points here. At negative 2, here's my c value. At negative 2, I'm at 3. That's the solid filled in dot. However, the limit as x approaches negative 2 is going to be, what happens is I get really close to negative 2, and there my fingers come together at this 2 value, at 2. So the limit there would be 2. 5 and 6, so limits that do not exist at the c value, at 4, and here at negative 1. Notice there's a big gap there, so the limit does not exist. The left side and the right side do not match up. The whole point of a limit existing is that you need the left and the right side to match up. So those are nice examples of that. All right, moving on here. What I'm talking about next is just basic continuity. Okay, so a lot of these problems here are asking, when is the graph continuous? And there's a whole lot of them here. I'll try to get them all to fit on the screen. That last one maybe get cut off a little bit. But again, I'm trying to figure out, where is the graph continuous? Now, basically, you got to factor it. Okay, so for like 37 here, and we're going to do all these. I want you to do all of them, but you could pause it and do all of them. When I factor this, there's what's left. Now, those x's are going to be removed, so essentially I get 1 over x minus 1. So what happens is 0, that's what canceled, the 0 on top and bottom, x equals 0 would make the top and bottom 0. That's a removable discontinuity. So that's obviously a disturbance in the graph, so that's going to be a whole removable discontinuity. But at x equals 1, I have a non-removable discontinuity, and that's going to be a vertical asymptote. We've talked a lot about that as well. 38 here, if I factor the top and the bottom, unfortunately, nothing's going to cancel here on 38. So I realize I have two non-removable discontinuities. I have one at negative 1, and I have another non-removable discontinuity at positive 1. So those are both non-removable discontinuities, means they're going to make two asymptotes. 39 is a good one because the bottom cannot be factored. There's a plus sign there. You can't factor that at all. So there's actually no discontinuities here whatsoever. That graph is completely continuous. you could be able to figure a lot of these out. Notice ones with the absolute value, those are going to create these gaps. So on the left-hand side, we're going to be down at -1. On the right-hand side, we're going to be up at +1. So that's going to create that gap there, and that's that's obviously a non-removable discontinuity, and that's going to happen at -2. So right down here is at -2 is where I have a non-removable discontinuity. They don't cancel, they don't reduce, they don't remove each other because of the absolute value bars, but it does create that gap at -2. Watch out for these piecewise functions as well. Remember, for the function to exist, I need them to come together. So obviously the issue here is at 1, and they do come together. Both functions at 1, I'm at 1. So whatever happens on the one side, the graph's a line, and then it turns into a parabola. But the whole point is that they do come together. 46 here, at 1 is also my issue. That's where there potentially could be a discontinuity. If I plug in 1, I'm going to get 3 down here. I'm sorry, I'm going to get 1. If I plug in 1 down here, I also get 1. So these two graphs are coming together as well. And that's the whole point. If your graphs don't come together at that value, then you're obviously not continuous. Here's the last couple of problems I want to take a look at. And these are just talking about our limits of infinity, okay? So, for example, this graph right here, 35, if I factor that, I get x squared over x plus 3 times x minus 3. So notice if you plug in 3, what happens is if I plug in 3, I'm going to get a 9 on top, but I am going to get a 0 on the bottom. Because I get, well, let me show you this. I get 6 times 0 if I plug in 3. 3 plus 3 is 6, 3 minus 3 is 0, but obviously that makes 9 over 0. So here the limit does not exist. The overall limit does not exist, but I want to be able to look at what happens as I approach from the right-hand side. So what's going to happen is at -3 and 3, I have asymptotes. So if I want to show you guys a graph of this real quick, go to the function here. Let me clear these guys out. I got x squared divided by x squared minus 9. And we'll do a zoom 6 real quick here. So now you see there's -3 right here, and that's creating the asymptote, and there's +3. So obviously if you look at 3, from the right side it's going up, left side it's going down, so that's why the limit does not exist at 3. But as I approach from the right-hand side, I could say the limit is going towards infinity. So for 35 here, the limit would be infinity on that right-hand side. So that's a good one to talk about there. Hopefully that makes a lot of sense there. 37 and 38, probably check what's going to factor, what's going to cancel, and you can figure out where the limit exists. So let's just do one more problem here. We'll do 37 real quick here. So if I factor that, I'm going to get x and 3. I'm going to get x and 1. That's a +3 and a -1. I think that's going to make that right. On the bottom, I get x plus 3. I get x minus 2. I'm just checking to make sure I factored that right. I believe that is right. Okay, so the x plus 3s are going to get removed. So notice when I plug in -3, I would have gotten a 0 on top and a 0 on the bottom. But now that that's removed and all I have left is x minus 1 and x minus 2, now I could plug in that -3 and see what happens. If I plug in -3, I'm going to get a -4 on top and a -5 on the bottom. Negatives cancel, and I do get 4/5. So my limit here would be 4/5. So there is an asymptote at -2, or at +2 right here. But I asked about -3, and it canceled as opposed to not canceling. That was non-removable. So I mean, I kind of went that fast. That's a quick recap over limits, but we are going to be having a test over limits. I want to make sure everybody's on the same page with how to find and how to work with limits and hopefully make limits fairly easy for you guys. So anyway, if there's any questions, make sure you ask me in class on Tuesday, and we'll start from there.